Good morning, everybody. Thanks for this opportunity to share my experience with you. So we probably know a lot about CX7. And the CX7 is high content imaging. It's also called Celomics. So if you have a new user, you're probably curious why it's called Celomics. So similar to the genomics and proteomics, Celomics is a quantitative way to do cell analysis. So basically, Celomics will do three things for us. First, we'll image acquisition, and the second, image analysis. The third, data management. And Celomics, the CX7 we're talking about, is quite powerful and reliable. So it has very strong features. For example, endows microscopy allow us to capture all the image we want, and it also has the 7 channels, so we can have 7 targets, and allow us to measure our targets by counts, by size, by intensity. Also, we can measure the overlap and distance between 2 targets. Also, as Shrina mentioned out, we can measure the selected cell. So we don't have to scale, analyze all the cell. We can select the cell that we choose. So here I will give you an example. My research really focuses on the contact detection. Sometimes I work on the globalization. Also include translocation, auto-visualization text. As you can see here, Celomics can measure many different things. So today, the example I'm giving you is the mitochondrial assay, and this data is from my previous paper, which is the Celomics RNA. So here we have analysis well with the kilogram detecting cells. So in the column 1 to 4 is PNSO, which is control. Column 5 to 7 is one treatment. 9 to 12 second treatment. Both can induce autophagy. So here is a target 1 is a wild target, and target 2 is a mitochondrial gene. So there are 4 steps will lead you to the data. So step 1, you focus on the cells and you target the proteins as shown here. So you decide you find your target cells and you find your target proteins. Step 2, you will select the cells and target proteins. So as we can see, you can set the parameter which can have the size value of your cell and the target proteins. I try. So the next step, you can tell the machine how much cell you want to scan, the population. And in this case, it scans 500 cells. And then the latter, you tell the machine which kind of measure you want for the machine to store. For example, the first one, to tell the target 1 the contact, we cannot see this target 1 over object area, and also target 1 object total intensity. Also, you can tell the machine to give the data, the target 2 by contact, by intensity. Also, the overlap between 2 targets. Okay, so here's the data. So by CX7, the Celomics, we have 2 sets of data. So first is a number data. We do the quantification, so you can get all the numbers. So in this case, here is showing the target 2, which is mitochondrial DNA. As you can see here, from 1 to 4 is control. So mitochondrial DNA is quite high. 8 to 12 is treated with the treatment that we use autophagy. So degrade the mitochondrial DNA is dropping. So as you can see here by color. Then you can explore the data to generate the graph. So next, you also can get image. As you can see here, you can have the image of the whole plate. And you can select the one well. As you can see here, it shows all the cells scanned with different field. We also can pick one field and the machine will tell you your other targets. This target, this is nuclear. Target 1 is body parting. Target 2 is not technology, and merge the image. So you can export all the image and the data to generate the figure. Yeah. Let's pay attention. Have you had any question?
Okay, so I was asked to give a brief overview of what I'm actually doing, and that's just what I'll do. I'll just say, this is what I'm doing, and without too much detail of how it's done and so on. And actually, I'm going to talk about the size. I've used the Salonix as well, but I have also used the size quite heavily, and I've used it for two different things. One is for analysis of in vitro cultured cells. So I don't know. This image maybe doesn't look great, but it's a higher magnification. I captured it with lower magnification. And I just wanted to look at, expression level of something. And even with this relatively low resolution, I got a clear result because there is actually a big difference. And the other thing I'm using is for staining and visualizing tissues, in this case, tumor tissues. And I mean, after hearing what Sharina said, maybe the Salomix could be actually a really good option for that. But for getting the data, it works really well. So these are the two things I'm doing, and I just have 5 slides or so where I'll just explain a little bit more of what I'm doing. So yeah, I'm using it for tissues. I don't know. It seems nobody else, I don't know, today I think was looking at tissues. So there was a keynote PowerPoint conversion. So some of these things look weird. But yeah, I'm using it for tumors because that's what I'm interested in. I just want to give a very brief overview of the tumor model, what we're actually seeing here. It's a simple subcutaneous tumor model. You have mice, you inject tumor cells into the mice, then the tumors are growing. And in this case, I'm comparing 2 different types of tumors. I'm actually not revealing the name of the protein here because it's funded by a company, and I'm not supposed to talk about it and it's recorded, so I'm just pulling it out, but it's not important here anyway. So I have 2 different tumor types. One that is the parental cell line, the other one that overexpresses a certain molecule. Then I get these solid tumors from the mice, harvest them, snap, freeze, fix, then do a staining procedure, and then I have the stained tissue, then I can look at the whole tissue. And I still find it very exciting because, especially for quantitative analysis, I mean, sometimes we talk a lot about how to quantify this and that, but once you start selecting small areas, the whole thing gets kind of that's a big issue when you would select an area. So I think it's really important to look at whole tumor. It's kind of the standard anyway now, I think, the people looking at whole tumors because it's pretty representative. Anyway, so these 2 images show tumors from the 2 different groups. This is the parental tumor where this molecule is not overexpressed. You can still see that molecule, but it's like an endogenous staining. And I've confirmed that this correlates with the vasculature. So this molecule is co-expressed there. But in comparison, when you're looking at the overexpressing tumor, you see actually this membrane pattern. So it's really on surface pretty much everywhere. And I think you really get a nice, you get the whole tissue, but you also get, when you look at this inset, you have pretty good resolution. The limiting factor is really, I mean, the way this is, the tiling is really incorporated in the software. So, even if you just read the manual, you can do it. From a practical perspective, the biggest issue is really, it is a bit hard to to put together the whole thing, because you have to go one tile here, one tile there. And, as I said, the autofocus, I don't know, it's just not working. But well, anyway, it works, but it's slow, and I don't know what they do differently. I mean, the size, nothing against those, but the Salomix, I mean, the autofocus just works essentially, pretty much, and good. So anyway, it's pretty straightforward to do the whole thing. The time limiting factor is to do the tiles, and then also the capturing itself takes some time. It depends on the resolution. You can get a really high resolution, then it takes forever, really, And when I do a pretty high resolution, like I think I'm doing like 0, like I forgot, like I think it's 0.3 micrometer per pixel or the other way around or so. I should know that, but it's a pretty good resolution, and that will take you like 10-15 minutes or so for a tumor of that size. If you want to go with the maximum resolution, it takes long, but it's not really not necessary. And even that, what I'm getting is probably more than I need. So you probably could do something like that in time. So that's the one thing I'm doing here, and I just want to show. Well, this looks really horrible. I mean, that was like, sorry about the titles. I just you do it in Keynote and then I export it into PowerPoint to pull it together. But it's not that important really. So the other things I'm showing here is actually how I process the stuff. I'll go quickly over that because I'm always using kind of my own environment to do these type of analysis. But still you need like a source image. I mean, that's still kind of the key thing for me. Like, I cannot take the image myself. I cannot write any code taking image. I really need the microscope. And the microscope has lots of features. I'm sure for doing analysis, but I do it myself. I'll just go through quickly. So what I'm doing is, I look at this image. In this case, I'm even doing like drawing a manual boundary. It's not too many tumors, so it's possible to look at it. Probably can avoid the two. You look at the high magnification, you see in this case it's a vascular stain. So I look at the vascular stain, and what I'm doing is it's also kind of like a pretty simple approach, but it works well for the purpose I'm doing. I'm then kind of splitting the tumor into smaller areas here essentially, and then each of those areas gets like an intensity value. So and that's obviously like one thing you can do with imaging, because when you do the whole tissue, then you're losing that information. So obviously for the microscope, the spatial information, as others have said before, is the crucial thing. So that what I'm doing here, and then you see, we know a tumor is heterogeneous usually. So you see some areas with more vasculature and some less. And then, if you do this whole thing for multiple channels, and doing 4 channels is straightforward with the microscope. It's really straightforward. You have like 4 channels available. The colors are available that you have like really minimal overlap, so you can very easily do 4 channels. If you want to do more, I guess it would get tricky, but for a lot of questions, four colors is a lot, I think. And here is an example where I'm looking at 2 channels. One is the vasculature, the other is this is laminin alpha 5. Laminin alpha 5 is actually like a laminin that is associated with the basement membrane, so you would assume it to be associated with the vasculature. And then I'm comparing here because I found there is actually more laminin 5 in this overexpressing tumors, and then I quantified for each vascular density. So then I have like what I was showing before here, like this type of thing, but I have it for multiple channels, and then I can say, for example, like if there is a high density of vasculature, is there also a higher density of laminin alpha 5? And in fact, that's the case. You go up there, and then you see like higher vasculature. There's the lamina 5 goes up, but important for this experiment is also that this molecule, if you overexpress, you have more laminin alpha 5, and you can do the same thing for others. I mean, so here I'm interested in T cells. Of course, it's like the whole project is like a cancer immunology project. And one important question here in this field is, can cytotoxic T cells enter the tumor, or are they blocked out? And in order to measure that, I did like the 3 colors same here of like the vasculature and this laminin, and then the T cells, because the idea was if you have laminin, that may block the extravasation of the T cells. And when you actually look here in this area where you have less laminin alpha 5, you have more T cells, but in this other area you have lots of laminin alpha 5, and you have lots of T cells. So the idea is essentially that this molecule is kind of blocking entry of cytotoxic T cells into the tumors. And again, I could do a quantification here, and I in this case I compared vascular density versus the density of the cytotoxic T cells here, which by itself is kind of interesting. I mean, it's kind of maybe not surprising at all, but it may be surprising in a way. Anyway, you get a higher vascular density, you get more T cells, but importantly, again, like this one tumor that is overexpressing this molecule we're interested in, the slope is much lower, and you really have a reduction of cytoplasmic density. And you can just do it, and I think it may even help sometimes reproducibility, because like when you're having, I mean, I'm not saying that the whole tumor is a bad thing. I mean, ultimately you need a whole tumor and something needs to be different. But it's possible that you have like two different effects, like the vascular density goes up and then there's two different effects. And when you then normalize that, like what you're looking for, like the CT density for vascular density, you may find a clearer effect that you wouldn't see when you're just pulling the whole thing together. Anyway, it's one way to do it, and that's what this confocal microscope can do. So you have a tissue and you can look at the whole tissue and you quantify it. I also want to, so that was the one part. This was like, this is like the second thing I was doing. Cell, I mean, Sharina always tells me I'm not supposed to do that here because I'm supposed to use like the cell omics, which is much more quickly. But as Jing said, you have like an exploratory phase where you just want to look at cells. I think, you do something, you stain, and you think, oh, like, what's going on there? I want to see it. And in this particular case, I mean, there was like a really strong difference. So like I looked at those cells in vitro. I stained them. It's again like this control cell, the other cell line is overexpressing molecule. And I looked at the laminin alpha 5 because I saw it in the tumors. I was thinking, is it directly related to is it a direct effect of the tumor cells themselves producing the laminin alpha 5? And when I looked under the microscope, under the microscope, I think it always looks better in a way than when you process. But anyway, I found it clear different on the eyepiece. And then I just captured a few images, and then I again used my own image analysis algorithms to quantify that. I saw a big difference. In this case, I probably don't even need the mix because I could just capture like one area in the center, and it's not very heterogeneous. It's pretty much the same. So I really have faith that this works well. But if I could really capture these tumor sections, the whole thing with the Salomics, and the Salomics can do it for me without, I have to manually do these tilings, that could be something I could be very interested in. So I will check with you on that. And that's pretty much it. Sure. That was, thanks, of course, to Sharina and her team, to help us do the experiments and support and so on. So I feel really happy and great support, and I'm pretty cool. Anyway, so that was it.
Thank you.
Just showing where I did.